A 31-gigabyte AI search index just fit into 4, but the thing that shrank was not an AI model. TurboVec reports that 10 million document vectors fall from 31 gigabytes of float memory to roughly 4 gigabytes. That distinction matters because model weights, a vector index, and a model's KV cache are 3 different piles of memory. Here is the original TurboVec page where the 31:4 claim and its exact scope are stated plainly. So this story has 3 layers: why vector search gets heavy, what TurboQuant changes mathematically, and what TurboVec actually ships. Semantic search starts by turning every document into a coordinate in a high-dimensional space. TurboQuant does not understand the document itself. It only compresses the numeric geometry produced after embedding. The raw memory equation is brutally simple. Vector count times dimensions times 4 bytes for each float 32 value. At 10 million vectors, even a normal-looking embedding dimension turns the search map into server-sized memory. Lower precision helps, but traditional quantization often brings 2 kinds of baggage with it. Google notes that full precision quantization constants can quietly add 1 or 2 bits per number back into the budget. Product quantization can also require a representative sample, clustering, and a codebook before the first useful index exists. TurboQuant attacks that friction first. It is designed to be data-oblivious, so the quantizer does not need to learn your corpus. The pipeline begins by preserving the vector's overall scale and transforming its direction with a shared random rotation. That rotation does not add meaning. It redistributes awkward coordinate patterns into a known, concentrated statistical shape. With that distribution known, TurboQuant can calculate Lloyd-Max bucket boundaries from the mathematics instead of fitting them to your private data. In simplified pseudocode, every stored vector goes through the same transform, lookup, and bit packing path. The first quantizer minimizes reconstruction error, but low-bit inner products can still become systematically biased. TurboQuant spends 1 additional bit on QJL, a residual correction that removes that inner product bias in expectation. The paper proves that the resulting distortion stays within roughly a 2.7 factor of the information theoretic lower bound. This is the paper itself, not a marketing diagram, and its central claim is online quantization with near-optimal distortion. But elegant mathematics is only half the story, because the viral benchmark came from software Google did not publish. The answer is clean. Google Research published TurboQuant, while the independent TurboVec project built an installable vector index around it. TurboVec is written in Rust, exposes Python bindings, and installs from the normal Python package index. The operational advantage is online ingest. Add vectors now, search them now, without a separate codebook training phase. That is why the 31:4 result is more interesting than a compression ratio alone. The index remains usable as it grows. TurboVec also publishes platform-specific search results, rather than pretending every processor gets the same speedup. TurboVec can also honor an allow list inside its search kernel, so forbidden candidates are not scored and discarded afterward. For private retrieval, the practical appeal is simple. TurboVec can run on your own machine or inside your own VPC. A production vector database is also adopting the idea, but Qdrant explicitly adapts TurboQuant for real-world embedding behavior. That wording matters. Qdrant's implementation extends the research instead of presenting the paper as a drop-in production product. Now, for the other memory story, TurboQuant was also tested on the KV cache used during long language model conversations. A vector index remembers your corpus, while a KV cache remembers intermediate attention state for the current context. Google reports that 3-bit TurboQuant reduced KV cache memory by at least 6 times on its tested long context workloads. On the evaluated benchmarks, Google says the 3-bit cache preserved model quality without a measured compromise. Google also measured up to an 8 times speedup for attention-logit computation on an H100 with 4-bit TurboQuant. Read that label carefully. 8 times applies to one attention computation, not an 8 times faster chatbot from end to end. Google's own article separates the vector search result from the KV cache experiments and shows the exact benchmark framing. The honest version is stronger than the viral version because every number now has an owner and a boundary. Before replacing an existing vector stack, I would test recall, peak memory, ingest speed, filter behavior, and latency on the real corpus. For KV cache use, I would separately validate model quality, context length, hardware support, and total end-to-end throughput. TurboQuant's real breakthrough is not a magical ratio. It is removing the train-first bottleneck from high-quality low-bit vector compression. TurboVec then proves why implementation matters. Good mathematics only becomes useful when ingest, search, filters, persistence, and hardware kernels work together. So no, Google did not shrink a 31 gigabyte model into 4 gigabytes. TurboVec compressed a vector index using Google's TurboQuant research. Which would matter more in your system, fitting a larger knowledge base or serving longer conversations on the same hardware? Put your answer in the comments and subscribe if you want AI headlines separated from what the code and paper actually prove.